Okay, some more problems from section 9.1. This is number 19. And tell whether the series converges or diverges. If it converges, give it sum. And if we look at this, this is going to be the summation. It's already written out. E over pi to the n. So if I wrote out a few terms, I could say I got e to the pi squared, e over pi squared, e over pi to the third. So I just keep multiplying this by e over pi. So it's obvious that this is my a sub 1, e over pi, and my r is e over pi. Okay, e is about 2.7 and pi is 3.14, so that's a proper fraction. So that means it's going to be, that's my ratio, which is the absolute value is less than 1, so it does converge. So another one of these great geometric series. Really, when you see a geometric series, you know, you're in heaven because you already have the interval of convergence, and we'll talk about that in a few problems. And you can find the sum quite easily. It's just a, or a sub 1, over 1 minus r. So again, remember the sum, I can write it over here, equals a over 1 minus r, as long as r is, the absolute value of r is less than 1. So there's my a, there's my 1 minus r, and I can write this, you know, as I could have multiplied the top and the bottom by pi, but what I did was I just wrote it as a fraction, common denominator being pi, so I got pi minus e all over pi, and then e over pi, so I could just cancel these out. I inverted and multiplied, but you could cancel this out. You get e over pi minus e, and that's your sum. And you could leave it like that, or you could calculate it out, but that's fine to leave it in terms of e and pi, two of our most famous constant numbers there, okay? All right, so that's number 19. Okay. And some of these I did on notes, and some of these I had to do this evening. These don't take real long. This is number 20. Back this up a little bit here. There we go. So here's number 20. Now, sometimes these are a little disguised, so you have to kind of fool around with them. This is the summation of 5 to the n over 6 to the n plus 1. And, you know, this looks kind of odd. It looks like, you know what's going to happen to this. But, you know, I remember my law of exponents. If I could get 5 to the n over 6 to the n, I could put them both in the parentheses, and I would be in good shape. And that's what I'm going to try to do. But I got to get rid of this 1, so I can get rid of this 1 just by breaking this up. 6 to the n times 6 to the first. All right? But we know that that's the same thing from our laws of exponents. And then I could rewrite this, and I could put this 1/6 in front. And now I got my 5 to the n over 6 to the n. And maybe it's hard to see what the ratio is, but I can combine those under parentheses. And now I can see I've got a common ratio of 5/6. I just keep multiplying by powers of 5/6. And I wrote a few terms out. And I had 1 over 6. If I multiply that by 5/6, I get this for... So this would be n sub 0. When n is 0, anything with a 0 power is 1. So 1 times 1/6 is 1/6. And then when n is 1, that's going to be 5/6 times that. When n is 2, that's going to be 5/6 squared times that. Or just multiply this by another 5/6. I keep multiplying by 5/6. So I can see that my a sub 1, or my a, is going to be 1 over 6. And my r, my common ratio, is going to be 5/6. 5/6 is less than 1, so it does converge. And the sum is going to be equal to, and I should have written down the formula again, S equals a over 1 minus r. So there's my S, there's my a, and there's my 1 minus r. And 1 minus 5/6 is 6/6 minus 5/6 is 1/6. So I just have 1/6 over 1/6, which is 1. So not too bad. Okay. Number 21 through 24, find the interval of convergence and the function of x represented by the geometric series. Now this is where we start to get into the nice thing about these, okay? A geometric series is a polynomial, which is very, very easy. Very, very easy to take the derivative or antiderivative of these polynomials. Okay? Functions like this are not so easy. So right now we're going to kind of go backwards, because eventually what we're going to do is we're going to try to take a function like this and write it as a power series. And that's going to be a lot easier to deal with as far as calculations, mathematical manipulations. So first of all, let's take a look at number 21. It was 2 to the n, x to the n. And what I did was I rewrote this as 2x to the n. And if I write it out, I got 1. And then when n is 0, I've got 2x to the 0 is 1. When n is 1, I just multiply. I've got 2x. When n is 2, I've got 4x squared. When n is 3, I just multiply again by another 2x. So it looks like my a sub 1, or my a is 1. And my common ratio is 2x. If I take 1 and multiply by 2x, I get 2x. Multiply that by 2x, I get 4x squared, 8x cubed, etc. So there's my r. Well, remember, this is going to converge if the absolute value of r is less than 1. Well, in this case, r is 2x. So that's going to converge, okay, when 2x is less than 1. The absolute value of 2x is less than 1. And I can write this as -1 less than 2x less than 1. So 2x is between -1 and 1. And then if I just divide everything by 2, I get x is between -1/2 and 1/2. So this is my interval of convergence. Right here, I can write it down like this. From -1/2 to 1/2. And that's my interval. It's an open interval, because that's less than. And that's my interval convergence. Okay? Now, if I go back and write this as a function, I just use my sum formula. Remember, s, the sum of the function, equals a over 1 minus r. So my a is 1, and my 1 minus r is 1 minus 2x. So there's my function. Basically, that's what this is equal to. The sum of all these is equal to that, because it's a geometric series. So there's my function. And there's the interval of convergence. So this function is true. In other words, this function equals this polynomial for this interval of convergence, not at the endpoints. And we'll be talking about endpoints and what happens at endpoints when we have open closed intervals for different types of expansions or power series. Okay? All right. So 21 is a good kind of preview of what we're going to be doing. All right? And we'll do some more in a moment.